Hello everyone, welcome to the 12th lecture of this second module on analog meters, and we are discussing a course on measurement and instrumentation. In the previous class we have talked about the conversion of these ammeters and voltmeters that we have discussed, including the PMMC meters. What we want to see that when these PMMC meters are converted to ammeter and voltmeters, the ability of these devices or these instruments are like to handle very small range of current or voltage, because all these PMMC tools, particularly the movement part, the coil winding is very small, right? So it can handle very less amount of current, and we have seen that in case of ammeters it is like less than 20 milliamp, and in case of voltmeter it is like 50 millivolt to 100 millivolt. Okay, so the coil winding of this movements is very small and very light, because of which it can carry only this amount of currents. Okay, now since the construction of an accurate instrument with a moving coil which can carry up to say 500 milliamp current or anything greater than 100 milliamp is basically impractical, because when you talk about that kind of massive current, it will be very bulky, and the load of the coil or weight of the coil itself will be very high on the instrument, so it will be very bulky in nature. Okay, so what we have to do is we have to see the provisions. We have discussed yesterday also that there can be certain provisions by which this low current carrying or low current handling ammeters or low voltage handling voltmeters can be converted to tool which can handle high current or high voltage respectively. Okay, so here is a basic idea like how to convert this PMMC tool into a low current carrying or low current handling ammeters into high current handling ammeters. Okay, so this is a basic idea where this meter, if you see, is nothing but a say PMMC or a de-arsenable galvanometer. So I am calling this just a basic meter. Okay, and this basic meter is simply shunted by a resistance RSH. Okay, so I am calling this shunt resistance as RSH and the meter resistance RM, and throughout this lecture these two terms will be used. Okay, so shunt resistance RSH and meter resistance RM, right? Now in this case, in this figure, okay, RM is the internal resistance of the movement, okay, which is nothing but the coil. Okay, RSH is the resistance of the shunt that you have added. Okay, the current, this Im is basically the current which is flowing through this meter, and this also represents the full scale deflection current of the movement. Okay, ISH is the shunt current, and this I value, which is basically is getting divided into ISH and Im. So basically this relationship ISH plus Im holds in this case. Okay, this is the current actually which we want to measure. Okay, or this is the current to be measured, right? So now when heavy currents are to be measured, the major part of the current is bypassed through a low resistance, which is known as this shunt. This is the shunt resistance. Okay, and if you see, this is the low resistance path. Okay, and this is the meter resistance. Okay, so the resistance of the shunt can be calculated using conventional circuit analysis. So if say this is current value is say I, okay, and say this current is flowing through this is say I1, for example, I am calling this ISH as I1. This I2 flowing through this meter will be simply this I minus I1, right? So this RSH is the low resistance shunt. So this RSH value is very, very small, right? Now the shunt resistance, if you see, is in parallel with the meter resistance. Okay, the voltage drop across these two will be same. Okay, because they are connected in parallel. So if you see, I am calling this say point A, and I am calling this point B, and say this is point C, and this is point D. Okay, now the voltage drop across AB, okay, will be, say VAB will be equal to the current which is flowing through this shunt resistance ISH multiplied by the resistance of this shunt, okay, RSH, right. So, this is the potential drop across VAB or potential drop across the shunt, okay. Since they are connected in parallel, this VAB should be equal to VCD, okay. So, VAB should be equal to VCD, and this VCD is nothing but, say, if Rm is the internal resistance of this basic meter or the movement, okay. So, this will be equal to Im, the current flowing through this meter, into its resistance, right. So, by these two equations, this ISH RSH, the voltage drop across AB will be equal to Im into Rm, which is the voltage drop across C, this terminal C and D, right. So, ISH RSH is equal to Im into Rm, right. If I have to calculate RSH, RSH will be equal to Im Rm by ISH, okay. So, this I am calling equation 1, okay. The shunt resistance I am able to calculate if I know this Im, ISH, the Rm, the meter resistance, I will be able to calculate what is the requirement of my shunt, okay. So, RSH from this equation, equation 1 is equal to Im Rm by ISH, okay. Also, this ISH is equal to the total current which is under measurement minus the meter current, okay. So, ISH, the shunt current, will be equal to I minus Im, okay. So, therefore, what we can write from, say, I am calling this equation 2, okay. So, if I will put this value of this ISH from equation 2 into this equation 1, what I will get is RSH is equal to Im Rm divided by I minus Im. Fine, and this is what this equation 3 says. Now, I have three relationship. One is the resistance of the shunt in terms of the two currents flowing into the circuit, Im and ISH, and the known resistance, the meter resistance, Rm is known in this case, okay. Similarly, the shunt resistance can also be calculated by subtracting the meter current which I can see, okay, from the current which is under measurement. This is what equation 2 suggests, okay. Now, by using these two equation, I have calculated, or we have came to one expression where I can see that the shunt resistance can be written in terms of only meter parameters, okay. The meter parameters are current flowing through the meter and the resistance of the meter, okay. So, I can write the shunt resistance value in terms of only the movements parameter Im into Rm divided by I minus Im. Only thing here is left is the current which is under measurement, okay. Now, if I rearrange it, what I will get is I minus Im minus 1 is equal to Rm by RSH, or just by again taking this one to this side, I will get I by Im equal to 1 plus Rm by RSH. Fine. So, this is the expression, say I am calling it 4, equation 4, okay. So, I by Im is equal to 1 plus Rm by RSH. Now, the ratio of total current to the current in the movement, which is the total current is I divided by the movement's current, which is Im, okay. This ratio I by Im is known as a multiplying power of the shunt, okay. So, this value is basically the small m or the multiplying power, okay. So, this m is equal to 1 plus Rm by RSH, okay. So, if you are aware of this value m, or if I give you a meter whose multiplying power you know, you can calculate the resistance of shunt in terms of this multiplying power m and the meter resistance. Okay. So RSH is equal to Rm by M minus 1. Fine. So the shunt resistance used with the coil shows in the ammeter or voltmeter may consist of a coil of resistance wire within the case of the instrument, okay, or it may be an external shunt having a very low resistance. So what I want to say is, say this is your meter, okay. So this is your meter which is measuring this Im. Now where to put this shunt resistance? Although in the circuit it's very easy to show, but in the practical sense where to put it, okay. So the shunt resistance basically can be used with the coil of this meter, okay, within the case of the instrument itself, or it can be also used as an external shunt with some low resistance values, okay. So on the online platforms you can find different shunts, okay, which is available to be purchased, and you can use it basically with your existing ammeters, okay, if you want to extend the range. So it comes as a kind of piece of certain material which has this kind of resistance, okay. You can use it in conjugation with the existing ammeter, okay. So let us try to understand the basic idea behind the shunt. What are the general requirement of a material to be used as a shunt? So any material cannot be used as a shunt for these ammeters, okay. So the temperature coefficient of shunt and the instrument should be low and should be as near to each other as possible, okay. So the temperature coefficient, this is the first and foremost requirement for the shunts material. The temperature coefficient of the shunt and the instrument should be low, and it should be same or at least similar, or should be equal as much as it can be, okay. The resistance of shunt should not vary with time, okay. If it varies, all your calculation will go wrong, okay. So they should carry the current without excessive temperature rise, because if there is rise in temperature, of course it will hamper or it will change its resistance, which you do not want, okay. So they should have a low thermal electromotive force, particularly with the copper, because copper is what your movement is made up of, okay. So usually a very standard alloy of copper, manganese and nickel, which is known as manganene, which has around 84.2% copper, 12.1% manganese and 3.7% of nickel, is used for shunts of this DC instrument, as it gives low value of thermal EMF with copper, although it is liable to corrosion and is difficult for soldering, okay. So the one more important point about these meters or these ammeters is the effect of temperature change in the ammeters, okay. So this will cause the temperature error, okay, and the temperature error can be eliminated when the shunt and the moving coil are made up of the same material and kept at the same temperature, and that's what I mentioned, that this is the first and foremost requirement for a material to be viable to be used as a say shunting material, okay, or shunting resistance, okay. This method is not satisfactory in practice, as the temperature of the two parts are not likely to change at the same rate. Whatever you use, they will change at different rates, okay. So copper shunts are basically avoided, as they are likely to be bulky, as the resistivity of copper is very small. Otherwise it would have been very good idea to use as copper as a movement as well as the shunt, okay. So what I have just mentioned is we can use manganene, okay, which is known as a swamping resistance, which has a negligible temperature coefficient, which has of course a resistance 20 to 30 times of the coil, okay, and then it is connected with in series with the coil, okay. So swamping resistance is sometime required. So additionally, a shunt of manganese is connected across this combination. So you have a meter resistance, you have a swamping resistance, and across it the shunt is basically connected, something like this. So you have this swamping resistance, this is the meter resistance, and this is the shunt, okay. Now you have this arrangement just to overcome the issues particularly arising because of the temperature, Okay. So, temperature plays very crucial role in case of the ammeters, okay, and that is how you try to tackle it. Okay. Now, let us see how voltmeters are made using this DC meters. Okay. So, a PMMC basic meter movement is converted into a voltmeter by connecting a series resistance with it. Okay. So, there you have seen that in ammeter you have connected a resistance in parallel. Okay. Here what you are doing is you are trying to connect a resistance in series with the meter. Okay. And this series resistance is basically known as a multiplier. Okay. Now, this combination of meter movements and the multiplier is put across the circuit whose voltage is to be measured. Okay. So, this is your meter and multiplier, okay, and this is now connected across the potential which is under a measurement. Okay. The multiplier limits the current through the meter so that it does not exceed the value of the full scale deflection. Okay. And therefore, this multiplier becomes very crucial for the meter to be saved. So, it does not allow very high current of or it does not allow to expose this meter to very high current. Okay. The value of a multiplier required to extend the value, the voltage range basically can be calculated mathematically, and let us see how to calculate that. Okay. So, before we calculate, let us assume that this is the meter current IM. Again, IM is flowing through the meter and this IM will be again full scale current also. So, I am calling as full scale deflection current of the meter. Okay. RM is the internal resistance of the meter, similar to what we have just seen. Okay. RS, this RS is the multiplier resistance. Okay. This small v is the voltage across the meter's movement. Okay. This small v is the voltage across the meter movement for current which is say IM. Okay, and V is the full range voltage of the instrument. Okay, this was the voltage which is the full range voltage of the instrument. Okay, now let us see this small v. This small v will be equal to the current which is flowing through the meter multiplied by the meter's resistance Rm. Okay, so I am calling this again in case of voltmeter this as a equation 1. Okay, now this V, the complete voltage across the instrument is basically the value of the meter current, and since this resistance of this meter as well as this multiplier are connected in series, so IM multiplied by RM plus RS, or say if you can go by other way also, this V is equal to this small v plus say I am calling this V1. Okay. So, this capital V is equal to small v plus V1. Okay, this V is IM into RM, and this V1 is nothing but this, since whole current is flowing through this RS. Okay, it is not like shunt where there was a different current ISH. Here the complete meter current is also flowing through this multiplier. Okay, so this is IM flowing through this RS. Okay, so this V IM into RM plus IM into the resistance of the series, this multiplier. Okay. So, IM into RS. All right. So, this is the total voltage. Okay. Now, rearranging this fact and finding the value of RS from this equation, what it will give you is RM is equal to V minus IM RM by IM. Okay. I have just taken this to this side and then found this value of RS. Okay. Now, just rearranging this, okay, what I will get is RS is equal to V by IM, okay, minus RM. Now, what I have just written is the series resistance, okay, or the multiplier resistance value in terms of the total voltage that this instrument is seeing and in terms of the meter parameter. Okay. So, I am calling this as equation 2. Okay. Now, the multiplication factor is in this case is equal to this V divided by this small v, okay, or M is equal to V by small v, and if you just substitute these values of V, which was IM into RM plus RS divided by this small v from equation 1 as IM into RM, what I will get is this multiplication factor is equal to 1 plus Rs by Rm. Okay, I am calling this equation 3. Okay, this small m is equal to 1 plus Rs by Rm. Okay, or the resistance of the multiplier, if I would have to say, Rs is equal to m minus 1 into Rm. So if the multiplication factor is say m, Rs will be just one value less than this multiplication factor multiplied by the meter resistance. Okay, so for the measurement of voltage m times the voltage range of the instrument, the series multiplying resistance should be m minus 1 times the meter resistance. Okay, and this is a very important fact, particularly about the extension of range of the voltmeters. Okay, the essential requirement of this series resistance or the multipliers are like their resistance should not change with time. Okay, similar to what was the requirement for the shunt resistance. Okay, the change in their resistance with temperature should be negligible or should be very small, or it should not change ideally. Okay, they should be non-inductively wound on for the AC meters. So the resistance materials used for multipliers are basically again the alloys like manganese and the constantan. Okay, the multiplier resistance used in series with the moving coil is usually made up of magnetin having a negligible resistance temperature coefficient that we have seen. Okay, since the series resistance of the multiplier is very much greater than that of the coil itself, the variation of the meter resistance due to temperature change are swamped by the resistance Rs itself. Okay, so you do not have external swamping resistance here. The multiplier itself can act as a swamper, or you can say that it has swamped. Okay, or the temperature change are swamped by the resistance Rs of the multiplier. Fine. Now this is about the range extension. Okay, what about the sensitivity of the voltmeter that we have just discussed? Okay, the sensitivity of a PMMC voltmeter is very crucial and is a measure of how much resistance the instrument offer per volt of the full scale deflection, or you can also say that the sensitivity of a PMMC voltmeter indicates how lightly this particular PMMC voltmeter is loading the circuit in which it is being connected. Okay, and this is equal to the inverse of the meter current, or 1 by Im. Since we have seen that Im is also the full scale deflection current, I can also say that the voltmeter's sensitivity can also be calculated by calculating the inverse of the IFS, or it is 1 by IFS. Okay, and the unit is ohm per volt. Okay, fine. So this is a little bit about the range extension of these meters. We will try to see if we can solve some of the or we can discuss some of the problems in the assignment. Okay, now let us try to see the errors in PMMC instruments. Okay, so PMMC instruments are highly accurate DC instrument. On this particular node we have started this PMMC. Okay, however, certain systematic and environmental errors cannot be avoided and they will affect the performance of these PMMC instruments. Okay, and some of these errors are coming due to the temperature, due to the aging of the permanent magnet that is there for providing the flux density. Okay, because of certain issues in the spring control, because of the friction, which is because of the jewel bearing setup that we have seen. Okay, there are calibration errors, zero errors. Then because of certain external factors like external magnetic field can also generate a certain kind of error in these kind of instruments. Then overload errors, since these instruments are polarity based, means you have to connect the positive to positive or negative to negative. There can be some man-made or humanitarian errors like polarity errors, which is of course very sensitive to DC instrument. Okay, so if you have the wrong connection, you may not get the correct reading. Okay, so let us see some of the errors very quickly. Particularly we will see this from the point of view that how this occur, can we minimize it, and what can it cause. Okay, so let's try to understand first errors due to temperature this occurs due to change in the resistance of the meter. Okay. So, but meter has different resistances, right? Like resistance of the moving coil can change with temperature. The springs resistance can vary, okay? Or since we have already covered the shunt and series connection of the resistor, so their values can also change. So, the multiplier or the shunt resistors value can also change, okay? So, mostly these materials are metallic in nature, all these coils or springs or the shunt resistors. So, they have positive temperature of coefficient, means the increase in temperature increases the resistance, which result in lower current, and this will lead to under reading of the actual reading. Okay. So, mostly the reading will be less as compared to the normal readings. Okay. This can be minimized again by using magnetin or the constant turn resistors which have a low temperature coefficient. Okay. Or you can also, there are certain provisions to provide temperature compensations. So, by providing on device or in instrument temperature compensation, it can be at least minimized. Okay. The second error is because of the edging of the permanent magnet, which is quite obvious, because when you take use of this permanent magnet continuously, of course, because of the edging thing, okay, there can be certain errors. Okay, this edging can be because of or the errors can be not only because of edging, although it looks like edging, because of the lot of use of say across a temperature cycle or due to certain mechanical shock. Okay, this edging of the permanent magnet can result in the reduction in the magnetic flux B. Okay, and we have seen the deflection torque which was proportional to the current, but at the same time it was also proportional to the magnetic flux in the air region, right? So, if there is a decrement in the magnetic flux, definitely there will be decrease in the deflection torque. Okay, and again the result will be under reading. Okay, it can be minimized by using alnico or some advanced magnetic materials or magnets, like based on rare earth materials, like I have mentioned one example of permanent magnet like neodymium iron boron compound NdFeB in different composition. Okay, and it can also be minimized by periodic calibration of the tool. Okay, so regular calibration can help in improving these errors. Okay, so then third kind of error is the spring control error, and the basic cause is the fatigue or creep of the control springs. Okay, and this will basically result in incorrect controlling torque, and when you have incorrect controlling torque, what can happen is basically the meter may not come to its original position in the stipulated time, and because of that you may get a good amount of error in your measurement, which may be far away from the actual readings. Okay. This can be minimized by using high quality phosphor bronze springs, or edging treatment can be done during the manufacturing. Okay. Then another kind of error is the frictional error, and the cause is again the bearing friction because of the dual bearing setup used. Okay. It can be also due to regular uses, and in the regular uses there can be dust accumulation, or if you are not properly lubricating, these are mechanical parts. So, because of the improper lubrication also this frictional error can occur. Okay. The effect is simple, like pointers will not move freely, and hysteresis and sticking is possible, which is very unrare in case of PMMC tool otherwise. Okay. Minimization can be done by using special or advanced suspensions like taut band suspension. Okay. Or there should be certain provision where you can have regular cleaning of the instrument, and nowadays a lot of IP ratings has came like IP67, 68, right? So, where you can actually make the devices which are dust proof, right? So, there are then other errors like calibration errors, where the cause is incorrect series or shunt resistor values, or the improper initial calibration of the device. Okay, and the effect can be there can be several effects, particularly you can have a uniform scale shift which is very difficult to find. Okay, this can be again minimized by precision register which is being used, or by doing regular calibration of the instrument. Okay. Then zero errors is what these PMMC instruments are susceptible to. Okay. This is because of the mechanical misalignment mostly, but then permanent deformation of the spring or shock during handling of the tools is some of the causes behind this zero error. Okay. And the effect is like pointer will not rest at 0 when input is 0. So, it will show certain value basically which is not the actual value of the instrument. So, there is no input, but then also you have certain kind of output which you do not want or which is not desirable. Okay. So, this can be minimized by adjusting the screw which is known as zero adjust screw. Okay. Then by careful handling, where you take care of the instrument and you do not allow any external shock during handling. Okay. So, these are certain ways by which you can at least minimize this zero error. Fine. So, then there are other errors like external magnetic field errors, which is unavoidable. So, nearby magnetic fields from the transformers, motors, etc. can hamper the magnetic field induced in the permanent magnet available in the instrument. Okay. So, this may result in additional deflecting torque which is not desirable, and it can lead to incorrect reading. Okay. Minimization can be done by using magnetic shielding. This magnetic shielding are mostly done by using materials which will have fast magnetization and fast demagnetization also. So, in these cases soft iron can be used. So, that is a perfect example of a material which can be used for covering it or say protecting it from external magnetic field. Okay. Then we have overload errors, which is because of the excess current flowing in the device due to overload. Okay. This can result in the coil heating or permanent damage or loss of the calibration. So, this can be minimized by using protective series resistor, or there are other things like fuses as well as other techniques to available which can at least minimize this overload errors. Okay. Then we have polarity errors. Okay. The cause is very simple. You have connected the meter wrongly. So, positive has to be connected to positive, or negative has to be connected with negative. By mistake you have reversed it, and that is basically causing this polarity error. Okay. The pointer deflects in the reverse direction possibly, and it can also damage your tool. Okay. So, basically it can be avoided by proper polarity marking. Okay. Or it can be protected by using certain kind of diode circuits. Okay. So, diode, you know that it will pass current flowing through only in one direction. So, that kind of arrangement can be done so that to avoid any kind of polarity errors. Okay. So, these errors are very, very important in case of PMMC tools, and I am sure that while thinking about any of the instrument, you will be able to connect with the kind of error it can be prone to. Okay. So, let us try to see what are the advantages of PMMC tools have. Okay. And what disadvantages it possesses before we actually jump into the next kind of instrument. Okay. So, the advantage of this PMMC tools are like they have a very high accuracy, particularly for the DC quantities. Okay. Because uniform magnetic field is possible because of the utilization of the permanent magnet, and since this deflection torque is also directly proportional to the current, there is a linear torque equation. So, which can be very easily the deflection, we have seen the torque equation already, and we have found that this deflection was actually directly proportional to the current. Okay. So, or it was equal to say certain constant into current. Okay. So, you have a linear scale which is very easy for interpolation as well as even for interaction. Okay. So, this high accuracy is one of the important advantages of this PMMC tools. Okay. Their linear scale is another advantageous thing. Okay. They are very easy and accurate for reading as well as for interpolation or extrapolation purposes. Okay. Then it has high sensitivity because even for a small current it has good amount of deflection and minimal loading effect on the measuring circuit it poses. Okay. So then this kind of instrument consume very less power, okay, and they have very high torque to weight ratio, and because of this high torque to weight ratio, they have very quick response, as well as the dynamic performance of these systems are very good, okay. You do not have any hysteresis error in case of PMMC tools. So we have seen a number of errors, but we have not seen hysteresis error in this kind of instrument, okay. So permanent magnetic field is constant and there is no movement of the iron and other things available. So basically there is no hysteresis in this kind of defect in this kind of instrument, and they are effective. Eddy current damping is possible in this kind of instrument. So when you have this electromagnetic kind of damping, okay, you are very sure that there will be no oscillation. Of course, in the air damping system or in the fluid motion based damping system, there can be chances of having certain range of oscillation, but in this electromagnetic damping, which is basically because of this eddy currents, you can have a smooth and fast settling of the pointer. Okay, so these are the advantages of the PMMC tools. While whatever it does not produce, or whatever sense it is not helping, is basically the disadvantages of this tool. Okay, like they are only suitable for DC. So you cannot use these tools for AC measurement. Okay, it is, of course, it is subjected to different errors like temperature errors and other errors we have seen. Aging of permanent magnet was one of the cause of the errors. Okay. These tools are relatively costly because of the permanent magnets, high quality permanent magnets it uses, and the construction of these tools. So because of its construction, the cost is a little bit in the higher side. Okay. They are also delicate for construction, so they have a delicate construction, so they are basically susceptible to mechanical shock and overloads, and because of which there are certain errors that we have just seen. Okay, they have limited overloading capacity, so you cannot access the current to very high values. So there are certain rules which governs this overload capacity. Okay, and another disadvantage we have already seen, that when you keep this air gap more, or if you want to keep the pointer longer, there are stray magnetic field effects which can hamper its performance. Okay, so you always want to operate in the central part of the instrument, right? So this stray magnetic field, particularly at the end of the poles, are very crucial or can cause error in the PMMC tool. So this can be one of the disadvantages of the PMMC tool. So with this, we have covered the PMMC tools in good detail. Okay, we will be talking about another kind of instrument. Particularly, we will start with our discussion with the moving iron kind of tool. Okay, so in the next class, we will talk about moving iron analog instrument or electromechanical indicating tools. Thank you.